welcome everybody to another Wednesday NLP with Friends. We're really excited to have Eleftheria with us today. Hopefully we'll have a really nice discussion. Eleftheria is a fourth-year PhD student at the University of Maryland. And as you will come to discover in the next hour, her work focuses on detecting differences in meaning across languages and explores how they question common assumptions related to data in NLP technology. So with that, I'm going to turn it over to her. If you have any questions, please either add them to the dory or the chat, or we'll save them for the Q&A at the end.
Okay, thanks, Lynn, for the introduction, and NLP with Friends for having me. So let me share my screen. Okay, so good morning, everyone. Today we'll be discussing how do cross-lingual semantic divergences impact neuro-machine translation. So let's start by defining what parallel text is. Here we go. So parallel text is a text placed alongside its translation or translations, and there are various ways that we can collect parallel text. One of them is via human translation that can happen either via hiring human translators that are directly asked to translate source sentences into a target language, or we might ask them to provide them with a machine translation output and ask them to post-edit that. And this is generally a process that requires a lot of quality control and a lot of iterations in order to actually end up having good quality translations. So another approach for extracting parallel text is to resort to techniques that involve automatic extraction of parallel text. For example, we might have documents like translations at a document level, and we might want to sentence align them automatically. So of course, there we're making the assumption that we have one-to-one sentence alignment mapping, which might not always hold, as translators for a lot of reasons may just like decide not to follow the same sentence level segmentation ordering of the source text. So there might be noise that is introduced in that place. Another way of extracting parallel text is through the idea of mining the web, where we might just like treat sentences in two different languages as pools of monolingual text, and then we will try to find, we will hope that we are able to find exact translations through mining. And finally, another approach, and this is not an exhaustive list, of not automatically extracting text, but automatically generating text is using machine translation systems. So starting from monolingual text, we might use an MT to translate into a target language. So within the MT pipeline, human translations mostly are used for creating or evaluation data. And of course, this happens because, as you might imagine, this just does not scale. So we cannot just like hard human translations to translate all the source languages we might want to translate into the target language of interest and scale this up in the order of creating millions of training samples that our MT systems need to be trained on. So the automatic ways for extracting data are the ones that are used for scaling the parallel text extraction process. So the automatically extracted parallel texts are mainly used for training core MT systems, and the machine translated, the machine generated text is like in the MT pipeline is used in a meta learning, in a meta stage of training systems with like the popular projects of like back translation, forward translation that serve as a means of data augmentation for on top of the original training data that we have. So in this talk, we'll focus on the parallel texts that are extracted automatically. And as you might imagine, this automatic process of extracting parallel text might introduce various types of noises. And this is something that is known from prior work. And another thing that is known from prior work is that various types of noises impact neuro-machine translation. So there's prior work from Huda Karala and Philip Kohn from Johns Hopkins that studied the impact of various types of noises on new machine translation, where they defined like specific, like a set of noises that they found to be frequent in a web called English-German data. So they found short segments, segments that might contain non-linguistic content, parallel text in the wrong language, copies that were found to be very detrimental for NMT. So what we know is that noise is bad for training RMT systems, right? So in specific, there are particular types of noises that if they just represent a very small fraction of the original training data, they can still have very detrimental impacts on translation quality when training NMT systems on them. Okay, so what do we do now that we know that noise is bad? We just filter it out, right? So this is a standard approach that we have adopted in our MT pipelines. So we are pre-processing our data, we are filtering out noise, and then we are left with what we call parallel text. And at this point, we just hope that whatever we're left after filtering noise is actual parallel in the sense that they're exact, consist of exact translations into languages. So in this talk, we're gonna question this idea and look at how parallel this parallel text actually is. So let me give you an example here from English-French Wikimetrics data. So the English sentence is, after Caesar's death, he joined the party of Cassius. That is paired with a French sentence that I gloss here. That means after the death of the dictator, he's accused by Cassius of conspiring against Rome. So okay, clearly those are not exact translations of each other, right? But we can still see how they do not fit the definitions or like the types of noises that we talked about earlier. So we can see that there's still somehow topically related. So still we have some Angor words that connect the two sentences, for example, death and Cassius. So more or less they're topically related, but still they have some coarse meaning differences. They're not translations of each other. So this is an extreme example of unrelated sentences that can be found in our parallel text. Let's just now go and see what else is there. So that's another example again from English-French Wikimetrics data, where the English sentence describes the Maple Leaf Forever served for many years as an official Canadian national anthem. That's mapped, paired with the French sentence, the Maple Leaf Forever is an English-Canadian patriotic song. So that's quite of an improvement, right? So those are closer to be translations where they're actually partial translations of each other. They talk about the same event, but if we take a closer look at the two sentences, there's content in one language that is missing from the other. For example, I have highlighted here some content in the English sentence that does not appear in the French sentence and vice versa. And other than that, there's also phrases that are not exact equivalents, right? So for example, in the English sentence, the Maple Leaf Forever described as a national anthem, and the French sentence as a patriotic song. And those are kind of like, we're getting a sense of like they're closer to like being unrelated, but definitely they diverge in meaning. So we're getting better. That's assert content that has fine-grained meaning mismatches. So now that we have shown this, seen these examples, we can kind of like formally define what cross-lingual semantic divergences are. And that's a term that we use to refer to parallel sentences where the source and target do not convey the exact same meaning. And so the cross-lingual part refers to the fact that we are dealing with parallel sentences. So we want to compare and contrast meaning across languages. And we want to see how the semantics of the two sentences might diverge. So the outline of the talk is that, so as a promise in the title, like the main question we want to answer is how do semantic divergences impact UMS in translation? But before we dive into this, to answering this question, we have to firstly look at two other important questions. The first has to do with how frequent are those semantic divergences, right? Like, are they frequent enough so that we should care about them? And the second question is, how can we detect them, right? We cannot detect them. We cannot really understand their impact. So let's start by the first question. So we have to like go and look at the data to understand how frequent divergences are. And here I will be sharing a little bit about how we annotated semantic divergences in parallel text. This turned out to be quite a challenging annotation task for various reasons. The first reason has to do with the fact that we ourselves did not really want to go and hire professional translators for this task. So we went an annotator framework that can be used by annotators who do not have expert knowledge other than being bilingual speakers. The other challenge comes from the definition and the nature of the task itself, that divergences may vary in their granularity. And this is something that you probably already got a little bit from the examples that I showed, that a lot of things that might be going on and in different ways, and the intensity of them might also be different. And the final challenge is that, which is like a challenge for all annotation tasks, I guess, is that we want to have a reasonably good annotator agreement. And I'm saying the reasonable good here because this is a challenging task. So a perfect agreement would be probably more problematic than a moderate agreement for the task. So the annotation protocol that we had designed for this task was the result of like several iterations. And the final protocol had the goal of encouraging annotator sensitivity to subtle meaning differences. It was quite hard to do without trying to come up with ideas to force annotators to pay close attention to small meaning differences in the two sentences. So the result of this annotation exercise is a data set that we call REFRES, that stands for Rationalized English Trans Semantic Divergences. Pretty much explains itself. Like this is a data set that contains annotations of divergences for English trans data. And on top of the semantic divergence annotations, we also have annotations of rationales that I will explain what they are and how I use that term right away. So a little bit about the annotation protocol. So bilingual speakers were given an English and French sentence. Here we focus on Wikimetrics, and they asked at the first step to highlight parts of these sentences, or the two sentences that are different in meaning. And we call those rationales because at the second step, we ask them to make use of their own highlights to make a sentence level judgment. And the sentence level judgment, for the sentence level judgment, we provided them with three options: that of no meaning difference, which is like the perfect translations, what we hope we have in our parallel data; some meaning differences, which are like close to the fine-grained stuff that we described when I gave you the Maple Leaf Forever example; and unrelated, which is like sentences that just like convey different information, despite, for example, being topically related. So there are two things that are key here. One is the idea of using rationales, and it's key because if well, in theory, that's a process that human annotators should all anyways go through, right? Because they should just like be looking for differences that are fine-grained and like looking at spans and then come up with the final sentence level judgment. But it turned out that it was really important to actually force them to actually do that. And the second key design choice here was that we used 3 classes instead of 2. We started with a binary framework of, is this perfect translation or not? This is just so hard because of the varying granularity of the divergences. Different annotators may just decide to like, draw the line between what is good, what is not good, like differently, which means that some fine-grained mini mismatches might just like be annotated as perfect translations just because they're so bad unrelated sentences that will like go into the divergent class. So with this framework, we're able to improve annotator agreement on top of both like prior work on annotating divergences with binary frameworks and on top of our own initial stage of annotation protocols, protocol designs. Just for the record, starting with mTurk annotators, which has its own problems, like there's more noise introduced by that. And binary framework without rationals, we started with an agreement of like 0.2, and then we managed to like push this to 0.6 after changing the framework, and of course relying on annotators that we kind of like knew. So we moved a little bit far away from mTurk for this task. So in terms of results, we found that semantic divergences are frequent in refresh, and specifically they consist 64% of the annotated data. So if we revisit the first question, how frequent are semantic divergences? They're pretty frequent. So we found that only 36% of the times the parallel text was actually found to be parallel, was actually found to be exact translations of each other. Okay, so now I hopefully convinced you that semantic divergences are pretty frequent, and as a result, it's probably worth spending some time trying to figure out how to detect them. So moving,
I have a question.
Sure.
So in the previous one, you showed a 24 are not related. Do you have like examples on how these sentences look like, or like an idea what is the source of the systems that they are parallel?
So actually, the first example that I saw, the one before they made Holy Forever, was an example that was taken from the unrelated class. So what happens is that, well, yes, I have spot checked the annotated data. So what happens with the unrelated sentences is that there are a lot of sentences that are either structurally similar or topically related, but other than that, they just like convey different meaning. I think that this might have to do with the fact that the way that Wikimetrics was created using the laser embeddings. So I think that this is like pretty frequent, that sentences that may be like structurally similar, for example, they might just be anchored by the same dates or the same named entity. For some reason, they are mined using the laser score. But yeah, they were not like very clear, like even the unrelated sentences are not like very clear cut, you know, noisy samples that you might just like look at them and be like, okay, yeah, this is not. Sure. So moving to detection, I'll talk about two tasks for detection. One is a task at the sentence level where we have we want to take as input a parallel text, and we want to be able to say, okay, is this equivalent or divergent? And we want to do so without having access, without assuming access to human annotated training data for obvious reasons. It's really time-consuming task. The annotation task, I mean. And we also want to be able to identify divergences of varying granularity. So we want to be able to really tell apart the perfect translations from whatever is diverges in meaning in any way. So for that, I'll talk about Divergent mBERT. That's a framework for fine-tuning multilingual models. mBERT was the one that I used in my NLP 2020 paper because that was like the best at the time, but I can assume that this can be extended to like whatever whatever pre-trained language models are the best today. So the model will take as input a parallel text and will output a probability of the input text of being equivalent. We're doing that without supervision, but for now, we're going to assume that we have access to some set D that I will talk a little bit later about how we can automatically generate it. So we assume that we have access to some set D that consists of the X and Y contrastive pairs, for which we know that X is a parallel text that contains fine-grained divergences that are finer grained with respect to the divergence that may be found in Y. So both X and Y are parallel text, and we assume now that we have some notion about X being a better parallel text compared to Y. So having access to this set of contrastive pairs, we will fine-tune mBERT here to learn to rank the contrastive pairs, which, like, mathematically, this is realized by optimizing a margin-based loss where we want f of x to rank higher than f of y. So that's a sentence level task, and we can define at the same time another task that is a little bit more fine-grained, a little bit more difficult, where what we want is to, again, take as input the input sentence pair and output two sequences of equivalence versus divergent predictions that are predictions at token level. So the idea here is that we do not just want to know whether sentence pairs are divergent, but in cases, especially fine-grained mismatches, we might want to know, okay, what are the parts within the two sentences that diverge? So for that, we again are going to assume that we have access to some to parallel text for which we know the sequence of equivalence and divergent tokens. And again, we can fine-tune the pre-trained multilingual language model to the token level prediction task. That's like a typical sequence labeling task here. We want to optimize the token level cross entropy loss. So if we combine those two tasks together, we can come up with this multilingual variant of divergent mBERT, where we at the same time fine-tune the model to learn to rank the contrastive pairs, and at the same time we'll learn to optimize for the prediction of the tokens. Okay, so I promise that we're doing that without supervision. So now we will dive a little bit more into how we can create the synthetic data for this. So we're going to start from some seed equivalent first. This is here an English and French sentence that let's assume that we can find somehow some sentence pairs that we know are equivalent. So those equivalents are going to seed the generation of synthetic divergences that are fine-grained in nature. So subtree deletion is a specific type of synthetic divergence that we're introducing, where the idea is that we want to mimic divergences due to content that exists in one language but's missing from the other. So what we're doing here is that we take the English sentence and we randomly delete span within it, where here we also have some syntactic control so that we just don't randomly delete a span and destroy the structure of this sentence. So by deleting this span, we have automatically introduced a divergent in the opposite side, the thread side here, that I highlighted. So here, by this process, we have created synthetic training samples from both the sentence level and the token level task that I talk about, right? For the sentence level, we can contrast this synthetic divergent type with the seed equivalent. And for the token level task, we can assume that all the tokens within the two sentences are equivalent, except for the highlighted ones, because we know exactly at which part of the sentence we introduce the divergences. So that's one type. I'm going to talk about two other types that we create. The other one is phrase replacement, that is meant to mimic divergences due to partial mistranslation, phrasal mistranslations. So here we will again decide to replace a span within the English sentence with another span, where here again we have some control, some syntactic control to avoid creating very disfluent synthetic samples. And again, at the same time, we can create divergent divergent versus equivalent tokens for the token labeler task, VHS, assuming that the highlighted parts of the two sentences where we introduce divergences are going to correspond to divergent token classes. And finally, lexical substitution is the more fine-grained divergent type that we introduce, where here we introduce a divergent type at the word level, where we're just like pick one word from the English sentence and then decide to replace it with another one, where here we have some more semantic control. We want to replace it with a hypernym or a hyponym of it to mimic specific particularization, generalization, translation processes, which correspond to divergence that might be introduced by the human translation process itself. Okay, to sum up, I have started from a seed equivalent, and from the same seed equivalent, I talked about how we can create 3 different types of divergences. And as you might already realize by the process, each seed equivalent can contrast with each of those 3 different divergent types. So one way that we can make use of those as training samples is just to, like, in the learning to rank framework, we can just like use one divergent type at a time and just learn to rank the seed equivalent greater than each of the 3 different types. Or what we can do is to use what I call divergence ranking. This is a kind of like method that exploits the fact that the generation process of the synthetic samples introduces a partial ranking across the divergences. And what I mean by that is that, as you might notice, the lexical substitution types of divergence are more fine-grained than the other 2. So we can learn to rank seed equivalents higher than lexical substitution, and lexical substitution higher than phrase replacement and subtree deletion. That's another way of making use of the different contrastive pairs, right? So let's now go and see how do those models perform. We're going to evaluate them on the dataset that I talked about in the first section of my talk, refreshed. So for the sentence level prediction, the equivalent models are going to map to the no meaning difference annotated class from our exercise, and the divergences are going to be both the unrelated and some meaning differences. As I said, that we want to draw the line at the point of like we're only going to allow exact translations to be given the equivalent class. And the token prediction is evaluated with respect to the gold standard rationales that we have extracted in our annotation exercise, where we ask annotators to highlight the part of the sentences that are divergent. So results. Here I'm showing you the F1 results for the sentence level prediction task, where we compare with a laser baseline. The laser baseline thresholds the margin score between 2 sentences that are extracted from multilingual encoders at a specific point. We have tried different like thresholding laser at different points, and we cannot. This was like the best performance we could actually get. So what this actually shows us is that well, laser is not sensitive to fine-grained meaning mismatches, and that's kind of expected, right? Because we annotated the wiki metrics that it's extracted using laser, so that's kind of like something that we knew, but we want to reconfirm the fact that laser might be an approach that is typically used either itself or like in combination with other approaches for noise filtering, but noise and cross-lingual semantic divergence are a little bit different, which means that they kind of like require different methods for detection. So another thing that we see is that learning to rank each of the three different types of divergences that we created gives reasonably good performance on refresh, and the divergence ranking gives the best of it. So I will go briefly on over the results on the token level prediction task, where here I'm showing the F1 on the divergence, and everyone scored on the divergence class, the equivalence class, and the product of them. And we compare the multitask model with, just to put numbers in perspective, right? Because that's just, there are not lots of baselines here. We compared with a random labeler. And what we actually want to see here is that, okay, we tried to solve a quite difficult task that has a very fine-grained nature, right? Like detecting divergences at the token level is like quite fine-grained. The cross-lingual part of it makes it even harder. So we tried to solve this task without any supervision. We tried to just like create synthetic, like corrupt equivalence with synthetic types of divergences and use those token labels to learn a model that sequence label the two sentences. But we still see that the signal that we get from this like process of synthetically creating data can give us some sort of like useful supervision signal for doing better than random. So of course here, I think that there's a lot of more work that can be done to like just like push those numbers a bit further, and there's a lot of like recent work on explainable quality estimation that's kind of like has some connections with this token level labeling task. But yeah, as we'll see, the predictions of the token label can still be useful for helping mitigating the negative impact of semantic divergences on NLP, as we will see a little bit later. So let's sum up the chapter 2. Can we automatically detect divergences? Yes, we can. We can do that without supervision by learning to rank divergences. Key here is that in the synthetic generation process, we have introduced some priors, so like what we expect to see in the data, or some linguistic priors of the semantic divergence. We didn't just like randomly create some negative synthetic data. And we talked about 2 different task definitions for those tasks. So let's finally go and see how do they impact neural machine translation. So first I want to revisit a little bit what are the assumptions that we're making when using parallel text for neural machine translation. Here I'm giving you in the top of this figure, I'm giving you a perfect translation reference, target reference for a source French sentence. This is "your father is France." And the kind of like, hopefully, like you can see that there are like blue lines indicate that the signal is reliable for training empty systems at its time step. And then in the bottom of the figure, we see how just like changing one word within the correct reference makes the signal unreliable with the red dotted lines. So we'll just go through this example to like make it a little bit more clear. So typically when we train empty systems, we are optimizing for the token level cross entropy loss when we have a source sentence, like the French sentence I'm giving here, and a target reference that we assume is like the gold standard that we should optimize for. So let's see how we're optimizing for your parent or is France target, where we know that the word parent is a divergent token. So at time step t equal to 1, we condition the generation process on the source reference, and we optimize for a correct prediction. Your is a correct token, right? At time step t equal to 2, we optimize for prediction of a divergent token. So here's like one source of like unreliable signal that is being introduced. However, we condition the generation of this token on a correct source and target prefix. At time step t equal to 3, again, we optimize for prediction of a correct token based on our target reference. However, the unreliable signal is introduced by the fact that we are conditioning on a partially correct target prefix. This is your parent. And the same thing happens at time step t equal to 4. So hopefully we all realize that like how divergences can introduce unreliable training signals for MT, either via encouraging the model to predict incorrect target tokens or via conditioning the prediction of a possibly correct token to partially incorrect or completely incorrect target or source prefixes. So let's now move and see empirically how do fine-grained divergences impact NMT. Since it's not so clear whether they have like such a bad impact on NMT, right? Like with noise, it's like way more obvious. But here we saw that they might just like introduce good and bad signal at the same time. So, so a little bit on the experimental setting, we'll focus on Wikimetrics data for French to English translation, where we trained NMT transformer models and evaluate on TED. So the artificial setting that we're introducing here is again going to rely on the types of divergences that we introduced when we were talking about detection of them. So we're using the Divergent mBERT model that I talked about to just clear all the parallel Wikimetrics text of semantic divergences. We just want to have access to a perfect equivalent bytext. So having access to these, we're going to create 3 different versions of them, where for each sentence pair in the original equivalence bytext, we're going to introduce phrase deletion, lexical substitution, and phrase replacement, fine-grained divergent types that I talked about. So having access to those 4 different versions of the data, we're going to gradually corrupt equivalence with different percentages of noise, different types of noise. So we're going to corrupt with 20%, 50%, 70%, then we go all the way up to like training empty systems on the 100% corrupted data. So let's start by looking at how do NMT models that are trained on these different percentage of corruptions behave with respect to like the translation quality as measured by Blue. So we will have as a reference point the translation quality of the model that is trained on the perfect data, on the equivalence data, and then just look at how does the Blue degrade as we add different types and different percentages of divergent data. So those are the results, and I want to like kind of like break them down in 2 parts. The first is looking at what happens when divergences correspond to kind of like a small fraction of the data, and we see that they do not really have a significant impact on the translation quality. The drops are pretty small and insignificant. And the reason why I want to focus on this result too is because this kind of like contrasts with with whatever we talked about noise. Right, so we talked about noise, and we said that noise can just like correspond to specific types of noise, I guess, can correspond to a small fraction of the training data. I think it still have like very detrimental impact on translation quality. This is not something that happens with divergences. However, when they overwhelm the training data, we see that they have significant impacts on translation quality. Again, I want to look back a little bit on the chapter A, where we talked about how frequent they are, and remind you that we found that it is actually the case that fine-grained semantic divergences overwhelm the training data, right? So although we are on the synthetic scenario, if we were to like kind of like try and understand how would that map to the real case, we're probably somewhere in between 50% and 100. And to be fair, that was just an annotation exercise on English France, where I expect that the quality of the data is probably pretty good. So if we go to other language pairs, I would expect that we probably are closer to the 100% imperfect data than where we are with English France. Okay, so that was the impact that semantic divergences have on translation quality. Let's now look at how do they impact other aspects of NMT. So here I will see how fine-grained divergences impact the uncertainty of token predictions throughout different time steps. So again, the reference point is the equivalence model, and looking at all the other different types of divergences, we see that they increase the uncertainty of token prediction. So like we saw that training on fine-grained divergent data impact translation quality and also the impact on the output distribution. And the final aspect of NMT that we will look at here is how do the impact of on the frequency of degenerated hypothesis, where degenerated hypothesis here defined as repetitive repetitive loops that models can fall into at generation time, something like this is this is a building and this is a building and this is a building. So we saw here that if we compare with equivalence, all the types of divergences that we introduce increase this phenomenon, increase the percentage of degenerations, both in greedy search and in beam search. So let's revisit chapter C now. How do semantic divergences impact NMT? They had translation quality. They increase the frequency of degenerated hypothesis and the increased prediction uncertainty. So I don't think that I have time for this bonus slide. I'll go very briefly over it. So this is more of a question about, okay, now what? Like now we know that the divergences are frequent. We can detect them. They impact on NMT. What are we doing about it? So that's one way that you can go for is okay. Can we adjust the assumptions that we're making when we're using the data? So can we somehow incorporate integrate this assumption of parallel text not being as parallel when training into systems? And one way of doing so is via encoding divergence as token factors. I'm not going into details about this. You can check my ACL 2021 paper about this. And with that, I will very briefly summarize the talk and then conclude, I guess. So we talked about cross-lingual semantic divergences, which again are mini mismatch in parallel text beyond noise. And the way I like to kind of like look at the space of problems related to cross-lingual semantic divergences are kind of like depicted here. So one has to do with annotation of divergences, detection, understanding their impact, how can we integrate them and like make them part of our empty pipeline or like whatever other task we're using them, and just like making the assumption that they're perfect translations. And two more kind of like active areas of research for me related to cross-lingual semantic divergences, how we can refine them. So instead of just like changing our assumptions about semantic equivalence in parallel text, can we just make divergences more equivalent? And the other one has to do with whether we can characterize a little bit better and a little bit more precise the nature of them. So can we say something more about not just like whether two sentences are divergent, but in what ways are they divergent? So this concludes my talk, and I'm happy to take any questions.